You hear the clouds roar their throats out. You hear the rhythm of the drops on the roof. You hear the gutters quiver under the weight of their innards. You know it's raining outside. You tell your roommate that it's raining. He takes his headphones off and claims that it's just planes in the sky, pigeons with their little feet, and squirrels running through the pipes. He once thought it was raining, but he was wrong, and that day he couldn't go out to get a Mountain Dew. Poor soul still remains scarred. You fling the window open, and drops graze his eyes. He lets his arm out, and he's drenched by a battalion of drops. He's convinced, and goes back to playing Counter-Strike. A proof in its simplest definition is an argument that convinces a reader of the statement that it's about. How could something so subjective, dependent on the reader, and convincing could be the measure of objectivity in math? Let's have a little chat about that. This video is divided into 3 parts. First, what is the purpose of a proof? Spoilers, it is not just to show that a statement is true, but rather why it is true, which I'll try to illustrate with an example. Second, why do we teach proofs? Why are proofs important not just in mathematics research, but also in math teaching and communication? And finally, thirdly, why aren't we, yes, all of us, more obsessed with proofs? So, what is the point of a proof? A proof needs to follow logically from something we all believe to be true, and so it is a way to get to the common truth in a very certain sense. The flavor of mathematics is tied to the certainty that proof provides. Any claims that are made and are verified are sure to stand the test of time. There's no approximation or error tolerance in a proof. Even when dealing with probabilities, if the outcomes are random, the probabilities assigned to them are still certain. So the notion of the proof that we have built over millennia is a powerful tool to ensure that what we obtain in our hands is the truth and nothing else. But the truth of a statement is sort of a boring reward for the effort. In the current mathematical status quo, there are a lot of statements which people believe to be true, but they don't have a proper proof. Like number theorists often assume the generalized Riemann hypothesis in their works. So a proof isn't just a confirmation of truth, but rather a way to shine light upon the part of math that you might care about. Recently, I was thinking about this identity, but even when I found one proof of it, I kept on searching for more because some part of me was curious about how I could interpret this identity in a different way. I wrote this up in a blog post which you can read here, but let me just summarize it for you. A is any list of natural numbers. So let us take A equal to 1, 2, 1, 2. Here the sum of A is 1 plus 2 plus 1 plus 2, which is 6, and the length of A is 4 because it contains 4 entries. This quantity counts how many ways there are to move the elements around, that is how many rearrangements are there. We see there are 6 of those, as you can see on the screen. Finally, this quantity takes all the rearrangements and sums their last parts, which in our case is 9. And plugging these values shows that the identity indeed holds. Why is this true at all? The first proof that I present is by using a formula for the number of rearrangements. Once you have that, you can do some algebraic magic to show that the identity works. If you pardon a silly semantic distinction, to me this procedure feels more like a verification. You see this behavior when doing a proof by induction, wherein it feels like you are checking that formula or pattern holds rather than coming up with it. Much like how the nucleus and the ribosomes uphold the central dogma of the cell, and one can run experiments to study the mechanism of how this works, but it doesn't answer how such a system came about to be in the first place. Why is there this length floating around? And what is up with the sum of the last parts? And here comes the philosophy that I strongly believe in. In most cases, interpretation is more useful than a formula. If you can associate, say, a picture to your expressions, it will give you more valuable insight into their inner workings. So, let's do a quick proof, which I hope convinces you. If we replace each number in the list with a brick of that length, then stack all the rearrangements on top of each other, it gives us a wall with an area exactly equal to the sum of A times the rearrangements of A. We are interpreting the product on the left hand side with this picture. To see what is happening on the right hand side, if you take a list and rotate it, you send every element one step to the right and boot the last element to the front. Then the last part takes a lovely little stroll through the wall, creating exactly length of A copies. If you squint a little bit, you will definitely see that the list 1, 2, 1, 2 creates only 2 copies under rotation, not 4. But fear not, my keen friend, for it also contains double copies of the last part, which balances out the half strolls it takes. This proof only gives you the basic idea, and I would encourage you to try it out with an example of your own or read the blog post for more details. Once you feel good about it, I think you will appreciate why I find this proof more illuminating. It tells you how within rearrangements, you can make some by rotating others. This rotation is handled by this length quantity. This way of proof assigns semantics to each part of the expression, which I feel the formula of proof hides. Even though all of the proofs here are objectively true, they all have different flavors which appeal to a different aspect of understanding. So even the mathematicians will agree on the correctness of all of these proofs, they might disagree on which proof is the best explanation. Good proofs not only establish the truth of a statement, but also trace its development, how it came about, what does it mean on a very fundamental level. They not only fling the window open, but also tell you why it's raining. But there's a thread going through this tale, which is that you have any opinion what a proof should look and feel like. And yes, this is not something that we are born with. It comes from practice, exposure, and often the community telling you what a nice proof should look like. Mathematics, like any other discipline, is mired in its norms. But most of these norms have stuck around for a good reason, and they tell you how to do mathematics without breaking it. It is important to communicate these norms to students, but as is often the case, the teaching of mathematics is often conflated with the teaching of these norms. Notations and rules take precedence over the teaching of understanding, and in that journey the interest is lost. If you take your kid to a curio shop and the only thing you did was yell at them not to touch the trinkets, they would soon get frustrated. I want to make the crazy claim that proofs actually help us fix this problem. But before we employ proofs in teaching, we need to ask ourselves, what do proofs even talk about? Math isn't real, right? There are no walls with bricks like these. I could drone on and on about the Platonic ideal in mathematics, but I think mystification is a form of gatekeeping. So here's how I like to think about this. In general, any field of study is a study of objects. The kind of objects that you're looking at determines what that field of study is. So biologists study plants, biospheres, the nervous system, while chemists study zeolites, lipid layers, and whatnot. The objects that mathematicians study are a little less tangible. They're vector spaces, group homomorphisms, logical operators. These are ideas that exist, but you can't really sense them. So under this definition, if a probability distribution comes up while you're studying biology, that doesn't make your field of study math, unless you focus on the probability distribution itself. That's why lots of fields of study have mixed flavors because of the different kinds of objects that people are working with. The fundamental difference in the nature of these objects is what makes math communication an uphill battle. For most objects that people study in other fields, a normal person has some established context. However, for mathematical objects, no matter how fascinating they are, you need a certain level of background to be even motivated to think about them. I think of it this way. Say you work on the cell wall of some bacteria, and you meet a person who has never even heard of microorganisms. So you can't really start by saying you work in bacteria, right? So you have to take a step back and probably start at, you know how you get sick, right? It's because of these small living things that enter your body and how these things are covered and so on. And it's possible that at some point they lose interest in what you're saying because they think you're just making stuff up. Now to imagine what it's like for mathematicians, say the person also has never fallen sick, so you also have to explain that. So how does all of this tie back to proofs? Mathematical objects are those which respond well to proofs in the current way we do proofs. The trade-off that we have for the certainty of the proof is that we have to make our objects more abstract, and in some cases a little too abstract. It is almost impossible to prove rigorously what a brain will do, but what we can do is we can take the firing of a neuron, study its action potential, do some signal processing on it, and then this becomes mathematics, which has no loyalty to biology anymore. Anything that you prove in this region may or may not be applicable to the biological system that you started with. And yeah, this is how we got neural networks. And no matter how hard they try to convince you, neural networks don't have any loyalty to biology anymore. And this is why we should be teaching proofs. It gives students time to play around with these objects that they will never see with their eyes or feel with their fingers, but in some buzzing part of their brain, they'll feel it. If I ask you to imagine biology research, then you probably imagine somebody working in a lab and not slurping up textbooks. It's not enough to start teaching proofs in college because by then the disdain has already set in. We introduce proofs early on. Simple, easy proofs. Not as a means of getting to some ambitious truth, but to make our students friendly with these objects, which, like microbes, are invisible to the eye, yet so real. And to quote the Little Prince, what is essential is invisible to the eye. This brings us to our fateful end. Why should you care? Why should any of us care? The real world is brutal with its utter complexities, and the abstract objects of mathematics can barely begin to explain it. So, is there any usefulness to a proof? I believe so. Constructing an argument is how we teach each other. It is how we show different sides of the world to people who refuse to see it. The same elements that go into making a well-crafted proof also go into making a well-crafted argument, like speeches that change the world. And when every little pore of your time is bombarded by someone else's thoughts, every interstice filled with a scroll to another part of your feed, to the coast of comments, all ready with gasoline and torches. This forward momentum of our lives gives us little chance to think about things that really matter. Some people find their motivation to slow down in gardening, and some people find it in proofs. Each proof is an invitation from the mathematical community asking you to play around with some objects, to slow down and see how math works. People often get into proofs thinking they don't care about the math, and so they don't want to do proofs. But this is the exact opposite of what's true. Proofs are how one learns how to care about math. Your first day of working with a skill is going to be hard, but you will eventually see progress. Working with proofs and math is not a lot different. You might not care about abstract in the mathematical sense, but you do care about the abstract notions of friendship, love, and allyship, right? Mathematics is a fragile endeavor, as we have seen in the context of set theory and Russell's paradox. Good starting points and correct proofs are what makes sure that this program stays up and running. A correct proof in math is eternal, and then it becomes our responsibility to care. With so much misinformation in the world and with so much hate, it is only fair that we exercise our willingness to slow down and check the details, challenge ourselves, and sometimes even come face to face with evidence that disagrees with our beliefs. Mathematicians are often surprised by proofs that go against what they believe to be true, but in the end they have to kneel to the proofs. And even if we could practice a fraction of it in our world, to believe in evidence rather than ill-formed beliefs, I think that might be a good first step. We can learn from proofs how to be careful. If you were in a world that could crumble from the smallest crack of incorrectness, wouldn't you want to be more careful?